Welcome back to compiler construction. So as we announced in our last lecture, we are now leaving the front end and we'll take a closer look at the interface between a compiler front end and back end. So today's topic are intermediate representations for code, and one specific intermediate representation is what we're going to take a closer look at today, and this is tree address code. So first we'll give an intro to intermediate representation. Then we'll take a look at different ways to implement intermediate representation, so we can classify intermediate representations into different kinds. And then we can take a closer look at some of these classes. So the first class are graphical intermediate representations. So we'll show you how we can get from a parse tree, a syntax tree that we have derived from our parser results, to what we call an abstract syntax tree, which is a simplified form of it. But there are also other intermediate representations, so we'll take a look at linear intermediate representations, and one example for this is the intermediate representation used in the LLVM compiler toolchain. And we'll take a look at the implementation of different ones like tree address code and stack machines, and there are also hybrid approaches. So what's missing from our compiler? We have covered lexical analysis, syntax analysis, and semantic analysis so far, and our semantic analysis has left us not only with a syntax tree, but with what we've called an attributed syntax tree. So in addition to the structure of our program that was reconstructed and represented in our syntax tree, we now have a name analysis, so we know the definition and scope of symbols in our program. We have a type analysis, so we can check the correct type of expressions and assignments. And we have also created symbol tables. So a symbol table then just maps the identifier to a type and also to the position where this identifier shows up in the source code. So we're here, we have an attributed syntax tree. So our next steps in our general compiler toolchain would be to optimize and to generate code. So generating code obviously needs to consider information in our syntax tree. We know our syntax tree is a representation of the syntactic structure of the program we are trying to compile. But obviously we not only want the syntactic structure, but we want to execute our program. So that means we need information about the control flow as well as the data flow. And this implies that we need different levels of abstraction here. So we need some sort of representation for all of the knowledge that the compiler was able to derive from the stages we have analyzed so far, so scanning, parsing, type analysis, and this is a good idea to introduce a new representation here, and we call this an intermediate representation. So most passes in this compiler we're going to consider here are concerned with intermediate representations, so most passes consume the IR, and also most passes produce intermediate representations. The good thing about intermediate representation is that it's somewhere on a level between your source code and the machine code you're trying to generate. So this means that we can be more general, so the intermediate representation makes it easier for us to actually reason about programs and to configure and modify these programs in order to optimize them. And this can happen in a machine-independent way because we're still on a level that's abstracted from the concrete machine we're trying to compile for. So essentially, for every optimization we can implement on intermediate representation level, we know that this optimization can benefit a lot of different target processors. So not only the one we are currently thinking of, but maybe if we implement another backend, this intermediate representation is general enough so that the optimizations might also work for the other processors. So the intermediate representation in a compiler serves as the primary and also definitive representation of code. So in a compiler using an intermediate representation, we have additional steps between semantic analysis and code generation. And these additional steps imply that after semantic analysis, out of our syntax tree, we generate our intermediate representation. So with this intermediate representation, we could then directly generate code, obviously, but we can also try to optimize this intermediate representation code. And as you see by this arrow here going back to that step, This means we not only have one optimization, but we can have several optimizations that we execute in a certain order, one after the other. So we have these two additional steps: IR generation, which transforms our syntax tree, which we got as a result of syntax and semantic analysis, into our intermediate representation. And when we have this common intermediate representation, we can now optimize this, so we can perform generic, so non-target, non-machine level specific optimizations on that level. And there are a large number of different optimizations. LLVM literally has hundreds of them, and most of them are executed in sequence on the intermediate representation of our program. So how can we represent this intermediate representation in code or in some graphical form? Now there are three ways in general to do this. First, we have graphical intermediate representations. So graphical intermediate representation, as the name says, in code, the knowledge a compiler has extracted about that program in a graph, and accordingly an algorithm that we try to compile is expressed in terms of a graphical object or a number of graphical objects, so nodes in our graph, edges in our graph, or maybe lists and trees. And the parse trees we've seen so far are some sort of graphical intermediate representation. But this is still a very abstract level of description, because we want to go down, we also call this lowering, to levels that are closer to the machine, because ultimately we want to generate machine code, obviously. So there's also linear intermediate representations, and these more or less resemble some pseudo-abstract machine code, so assembler code, for some sort of abstract machine. So algorithms operating on linear IRs no longer operate on graphs, but they operate on this linear representation, which can be a text-based or a binary representation. So what's common with linear IRs, as the name says, we have linear operation sequences. These are very simple considering the basic operations they use, and so it's a bit simpler to work on them compared with graphs. In addition, you can have hybrid intermediate representations, so these combine elements of graphical and linear intermediate representations. So this is an attempt to get the best of both worlds, so the strengths of graphical IRs and of linear IRs combined, and to avoid the weaknesses. So for example, you could use a low-level linear intermediate representation to represent blocks of straight-line code. We've seen basic blocks before. And you could connect these blocks of straight-line code in a graph to represent control flow of our program. So far, we have obtained a syntax tree as a result of parsing an input using our grammar. So here we have one of our example expression grammars again, and we know if we want to generate a parse tree for that expression here, a times 2 plus a times 2 plus b, we can set up this combination here of non-terminal symbols here, which form the nodes of our tree, and terminal symbols, which form the leaves of our tree, and then we connect them here using edges, and these edges here are defined according to the rule in our grammar. So to be precise, the syntax tree is just the parse tree that our parser has generated, no matter if it's a bottom-up or a top-down parser. So what's the difference when we talk about an abstract syntax tree? Now, when you consider code generation here, you don't really care about all these non-terminal symbols anymore. What you actually want is to know which instructions here are operations to execute, and in which order they should be executed, and what the data flow is. So which data has to be combined, which data is coming from where. So for example, some data is coming from a variable here, some other data is coming from an immediate value here, and we have to combine them here. But still, we don't care anymore on the machine language level if this was a term in our original grammar or that one was an expression. We just need to know something is combined here together using an operator, and then this is combined again with something else with yet another operator. So we can abstract from our parse tree, that's why we call it the abstract syntax tree, to remove all redundant information, and this uses less memory and is faster to process. So when we try to get rid of all this extra information, we can reduce our parse tree on the left-hand side here to the simple as. So you see we only have sources of data like a variable here or constants here. We have operations, and we have indications of which operands should actually contribute to which operation, to which result, and finally what is the top result of our expression here. So the abstract syntax tree retains the essential structure of our parse tree, but eliminates all the extraneous non-terminal symbol nodes. What is important, of course, since the structure is identical to our parse tree, this means the precedence rules and the meaning of the expressions remain, because of course we don't want to change the semantics of our program just to make it easier for our compiler. But still, an abstract syntax tree is a near source level representation, and because there is a ref correspondence to a parse tree, we could also have our parser build an abstract syntax tree directly. So we've seen that trees provide something like a natural representation for the grammatical structure of the source code of our program, which was discovered by our parsing process. But they have a very rigid structure, so we have to work with tree or graph algorithms, which makes it less useful to use ASTs for representing other properties of a program. So one idea we could have here is to try to model this aspect of program behavior in a different way. And that can actually happen in compilers, that you have different types of intermediate representations. You have graphical intermediate representation and you have some sort of textual intermediate representation. And these can be used in one compiler at different stages for different tasks, depending on what representation would be more appropriate for the task. And of course, you need to be able to convert between these representations in order to ensure that you keep the same semantics here. So compilers often use more general graphs as intermediate representation, for example in control flow graphs and in dependence graphs. So one graph representation that's immediately useful is representing our as a directed acyclic graph. So a directed acyclic graph, or short DAG, can represent code duplications in the tree. So code duplication is something that we see here. So we evaluate the expression a times 2 twice. Well, if we save the intermediate result of our first calculation a times 2, of course we don't need to calculate the same result again immediately afterwards, but we could reuse this. So a DAG is a contraction of the est that actually avoids duplications of partial subtrees here. So you see in this est our partial expression a times 2 is contained twice here as an identical substructure here. So this means that a DAG node now must be able to have multiple parents, because we want to reuse these identical subtrees, and sharing these makes a DAG more compact than the corresponding est. So the DAG needs to encode an explicit hint for evaluating the expression then. So if we know that the value of a cannot change between the first and the second evaluation here, so between the two uses of a, then the compiler should actually generate code to evaluate a times 2 once and use the result twice. And that's exactly what happens when we try to transform this est here into a DAG. We find out that, okay, yes, this is duplicate. So essentially we know this multiplication here also implies that we have a value flowing upward here. So we can actually reuse this value here to give a result for this next multiplication here, so a times 2 times b. And we can use this also to provide the first operand here for our addition. So this is our additional node, which means we can eliminate the left part here because we have already obtained our intermediate result down here in the graph. But still our est is close to the source code. So compilers need additional details. For example, if you want to perform some tree-based optimization and code generation in your compiler, for this your source level tree lacks much of the detail needed to actually translate statements into assembly code. So if you have a source level est here, which we've just seen for another expression now, so we have an expression a minus 2 times b, so we have the operator precedence expressed here, so we first execute our multiplication of 2 times b, then we subtract the result of that multiplication from a, and finally we use this assignment operator here to copy the result of our expression into our variable w. We don't know where all this information comes from, so we don't know where a and where w comes from. So essentially, we would want to lower this information again. So we would want to add more detailed information, which helps us to generate code. And a low-level AST actually adds this information. So for example, instead of just having a variable name, we have something like value nodes. So value nodes imply that we have a value that's already in a register. We may have number nodes. So number nodes are known constants, which we might use immediately in code generation as immediate machine language operands. And then we can have additional nodes like lab or label nodes here. So these might indicate an assembly level label, which would generate a relocatable symbol in our linker later on. And we have an additional important symbol here, and this is our diamond symbol here. So this diamond symbol here is an operator that dereferences a value. So that's like dereferencing a pointer, because we know that, for example, some values are in memory at some locations here. And so what we need to do is we need to use this pointer here, and this pointer can have an offset because it's in something like a global variable table here. And so the value obtained and used by the diamond operator here treats this value as a memory address and returns the contents of memory at that address. So in C it would be the dereferencing or asterisk operator in front of a pointer. So what we're doing here is, for example, we have a variable a here, and this variable a might be contained on our stack in a stack frame. So this means we need to figure out the address of our variable a, and that may be contained in a register which might hold your stack pointer, but it's not directly at this address, but it's at an offset of minus 16 bytes from that address. So what we need to do to get to this value of a here is we first need to get the value of our stack pointer here, and this might be completely machine independent still, because we can actually determine the layout of this stack whichever way we want as a compiler, more or less. There are some hardware restrictions, but not that many. So we have determined, okay, this variable a is at offset minus 16 in our local stack frame. So what we do is we add our base pointer and the offset. This gives us an address here, which we have to dereference again. And we could do the same for our variable b here on the right-hand side. So b might be contained in some global address space, so it might be now a data segment of our program, and might be at an offset of plus 12 from the base of our data segment. So we might use an offset from a label here, we add them together, and then dereference this to get the value of b. So essentially all this dereferencing here is important because it connects our AST to actually real-life requirements of our memory system here. But we've seen that we can use graphs for different uses here, and one very common graph used in compilers is the so-called control flow graph. We've already seen in our previous lecture that the most simple unit of control flow in a program is a basic block. So a basic block is a maximal length sequence of straight line code, so branch-free code, which means you can only enter a basic block at its beginning, and you can only leave it in one location, usually at its end, which may contain a branch instruction. So this means the instructions inside of a basic block are always executed together in sequence, with some exceptions. So if an operation obviously raises an exception or something, so it tries to access an invalid memory address, or it tries to divide by 0, then your processor might actually interfere and terminate that basic block early. But in regular operations, so if everything is correct, then you always have this uninterrupted sequence of instructions in your basic block. So we know that control flow always enters the basic block at the first operation of the basic block and exits at the last operation. Now a control flow graph, or simply CFG, models the flow of control between the basic blocks of a program, and a CFG is a directed graph, so it contains nodes and edges again, and the nodes in our graph correspond to basic blocks, whereas the edges of our graph correspond to a possible transfer of control from one block to another. So this models, each edge in our graph models how we could move from one instruction to the next using a jump, a conditional or an unconditional jump, for example. So, in contrast to the EST, the control flow graph provides a graphical representation of the possible control flow paths at runtime of our program. So this differs significantly from a syntax-oriented intermediate representation such as an EST, where we only have the grammatical structure. So let's look at different typical structures here. So one structure here would be a while loop, so just while and some condition, we execute statement 1, and if we exit this loop, we then finally exit statement 2. So a control flow graph would look like this. So we have a while, then we have a statement here, and that statement returns to the top of our loop because we have to check the condition at the start of our loop every time we run through the loop, because that might have changed. And well, when we finally exit the loop, we then go to statement 2. So these are the possible control flows here. Either we can go inside of our loop body here and then start at the beginning of our loop again afterwards, or we can finally exit the loop and end up here. So if you would just construct the EST for this loop, this would just be acyclic, because it would just describe a while with a statement block below it, and then we don't imply that we execute this multiple times. And we can also build this for an if then else condition. So here we check a condition with using an if, and if this is fulfilled, we execute statement 1, otherwise we execute statement 2, and in any case, after either statement 1 or statement 2 was executed, we continue down here with statement 3. So this is described in that way in our control flow graph. So essentially we have two choices to make. So either we can go to the left here to statement 1, or we can go to the right to statement 2, but in both cases, after statement 1 or statement 2 have been executed, our control flow joins again here and will continue in both cases with executing statement 3. So our control flow graph is an additional useful intermediate representation that concentrates on a different aspect, the control flow, and compilers typically use this in conjunction with another intermediate representation. So our CFG represents the relationship among blocks, basic blocks of code, and the operations inside of a block can be represented using another intermediate representation, such as an EST on expression level, or a DAG, or one of the linear intermediate representations. And the resulting combination would then be a hybrid intermediate representation. Many parts of a compiler actually rely on a control flow graph, either explicitly or implicitly. So optimization usually begins with some sort of control flow analysis, which first constructs our control flow graph. Instruction scheduling needs a control flow graph to understand which instructions can actually occur one after the other in our control flow. So it needs to understand how the scheduled code for individual blocks can work together or flow together. And also, if we want to do register allocation, finally global register allocation for our target, we need a CFG to understand how often each operation might execute, so which operation using certain registers might make most sense to assign these registers to, and where to insert loads and stores for spelled values to reduce the memory access overhead in our generated program. But of course, there's more to graphs. So we can also have dependence graphs. So we've seen a representation of syntactical structure in the EST, we've seen a representation of control flow in the CFG, but we can also represent data flow in a graph. And this means we want to represent the flow of data from the point where a value is created, which we call a definition or def, to any point where it is used, or simply shortly called a use. And this data dependence graph, which we're going to detail now, this embodies this relationship. So a node in our data dependence graph represents operations. Most operations contain both definitions and uses, and an edge in our data dependence graphs connects two nodes, so it implies the data flow here. So we have one node that defines a value, another one that uses the value, and an edge that connects the two. Dependence graphs are drawn with edges that run from definition to use, so we can actually find out in which places a value is generated and in which places then we actually refer to this value. So let's look at an example for a dependence graph. To capture the data flow, we need to extract the data flow from some sort of intermediate representation. So here we've chosen a linear low-level intermediate representation of a tree, which makes it a bit simpler for us to look at it. And so we have the linear code in some sort of intermediate representation for our expression here, a times 2 times b times c times d, and this is again assigned to a. So we see we do a number of things here, like we load, for example, some offsets from our base register here into another register. We load constants into registers. We load a set of different variables into additional registers here, and then we execute operations, like in this case only multiplications on different combinations of registers, save them again to some intermediate register, and finally store the value of our result to our register here, which is a base register with the offset of a. So let's now construct our data dependence graph here. Let's first indicate in our linear IR code where actually values propagate here. So for example, our register A is used again, so this is loaded here in our line 1. This is used again in line 6 as one operand for the multiplication, and then this register A is again used here as another operand of the multiplication. Or for example, this register B we loaded here from this address is used down here as a second operand of our multiplication in line 7. And then we can continue, like we can add dependencies for C. So we see our register C is used down here. Again, our register A, which holds an intermediate result, is then reused here again as an operand. And we can also see the use of register D and register A in instruction number 9. And finally, this result here in register A is then used as the operand of our store instruction to store our information here into the variable in memory. So we start with the first register, which would be our base register, RARP it's called, and we know RARP is relevant to instruction number 1. So these are just the line numbers here in our linear IR. And we can also use it in instruction number 3 and 4 and 5. And finally down here in instruction number 10. So it's all just the occurrences of RARP here as an operand of our intermediate representation instructions. So now we can look at the data that flows inside of our program. So where does the data we generate in line 1 here actually end up? So we've drawn these arrows again, so we know this RA from line 1 must end up in line 6. And that's why we add this arrow here. So now we can add all the other arrows here. We know that to actually execute this instruction here, this IR instruction in line 6, we also need another result. We need the result of loading our constant 2 here in line 2. So line 2 and line 1 are needed to get the values that we need to execute the multiplication in line 6. Line 6 now propagates RA to line 7, and line 7 also needs RB, which was loaded in line 3 here. So line 7 propagates its result to line 8, and line 8 needs RC from line 4 also to do the multiplication. And finally, we propagate that intermediate result here to line 9, where it's reused, and it's multiplied together with RD, which was loaded in line number 5. And finally, this value of RA is now propagated to line number 10, which ultimately stores it to memory. So there is some interaction between the control flow and the dependence graphs. So references to an element here, which we have an example code, which is just an array indexed by I, so we call this array A. And these references are shown deriving their values from a node that represent prior definitions of A. So this means when we have something like a loop here, we can connect all uses of A together through a single node. Now, without any sophisticated analysis of these subscript expressions here, the compiler can actually not differentiate between references to individual array elements. So we need, if we have something like a of I, an array in the element that's accessed, we need to be able to reason about the value of I here to actually figure out if there's a data flow between this array element or if it was just an access to a different array element here. So let's try to construct our dependence graph for our program with this loop and the array in it. So we start looking at line 1, and we see line 1 declares a variable x and initializes it to 0. So this value of x is used again in line 5 of our loop. Now x is just a standard scalar variable, so it's not an array. So what we do here in line 5, we read the current value of x, we add something to it, and we update the value of x. So line 5 actually is dependent on itself because it reuses the old value of x to calculate the new one. Finally, of course, this value of x is also used in line 7 down here when we print it, so after we exited the loop. So what else can we see here in terms of dependencies? Our second line here initializes our array element counter to 1. So this array element counter I is used in line 5, of course, because we access this element I here in line 5. It's also used in line 3 because we need to check the array element if it's still inside of the range of our array. And it's used in line 6 because we update our array element counter here by incrementing it. And finally, it's also used in line 4 because here we actually check if the value of our current element in the array at position I is actually larger than 0, and only then we add it to our sum variable x. So what other dependencies show up here? Now we look at backward dependencies. So whenever we execute our loop one more time, we reuse the values from the previous loop iteration. So for example, if we increment I here in line 6 and go up here again, we reuse this updated value of I to check the value of I in a loop. So we have this edge here in our graph. So you can see that the values for I in line 3 can either come from line 2, which would be the initial condition when we enter our loop the first time, or it can come from line 6, which would be the update of our loop counter here of our loop condition. Of course, line 6 increments I and assigns it to I again, so we have a dependency from line 6 to itself again here. What else do we have? Now, this loop counter here is of course the loop counter we use in the next iteration to access our array. So we've incremented the loop counter to access our next array element. So we have a dependency from line 6 up to line 4 here. And you see that line 4 now also has two dependencies, so it can depend on the initial index value, which we've set in line 2 for the first iteration of the loop, or for any updates we calculated in line 6 for subsequent iterations of our loop. Well, finally, of course, we have our array, this array A. We haven't initialized it here, so it just comes from outside. So our array A is used in line 4 for checking the value of the array element, and in line 5 for actually providing the operand to the addition here. So these are all the data dependencies in our short piece of example code. And you see what's important when you model a loop here as a data dependence graph. You see that values can not only come from outside, but they can also be updated inside of a loop, and we can actually have a dependence from one line of intermediate representation code or code to itself, because we update the value of a variable, for example, by incrementing it or by adding something to it. So this is what happens in lines 5 here for x, and in line 6 for our loop variable I. So what else can we do in terms of intermediate representation? So we've already talked about linear intermediate representations, and we've seen a very simple example of one already in the previous slide. So a linear intermediate representation is an alternative to graphs. So linear intermediate representations represent your code as a sequence of instructions that are all executed in order of their appearance, so usually from top to bottom if you would print them or write them on a sheet of paper. So linear IRs used in compilers are actually, well, at least looking very close to assembler code for an abstract machine, but they have some differences here. So linear IRs must include some sort of mechanism now to encode control transfer, because we don't have this graph anymore that shows us our control flow graph where transfer is actually changed, or where control is transferred in our program. And so our control flow in a linear intermediate representation models the implementation of control flow on a target machine. So we can benefit from the fact that most target machines behave very similarly in terms of control flow. Linear codes usually include two sorts of control flow. Either you have an absolute change of control flow, a jump in machine language, or you can have a conditional branch, which we would use for checking a loop condition or an if condition. So this control flow information in a linear IR just indicates that a basic block starts or ends. So that's the condition for a basic block. You've known already that there is no change of control flow inside of a basic block. So a block ends at a branch or at a jump, or it can also end just before a labeled operation, because even though that block at the beginning doesn't decide to change the control flow, it can still mean that we can jump to the instruction from somewhere else that directly comes after the end of our basic block. So again, there are different types of linear intermediate representation. So these types actually differ in the amount of operators that's provided for each instruction. So we have so-called one-address codes. These model the behavior of so-called accumulator machines or stack machines. So essentially you have one register or one data structure, which is a stack, which is separate from our variable stack, so an operand stack in a machine. And this is always used to accumulate results. So all, for example, arithmetic operations have the accumulator as one of the operands and also as the destination register. So we can say add variable b to the value of our accumulator, or add a constant 2 to the value of our accumulator, but we always have to involve the accumulator in this. So this one-address code style of linear IRs exposes the machine's use of implicit names, so a compiler can actually generate very tailored code for this. And one-address code is very compact because we don't need to specify a large number of operands for each operation here. We can also have two-address codes, so these would model a machine with destructive operations, so we can have two, for example, registers as source operands, but our machine would actually imply that one of the two registers would also be the target register. So we can add R1 and R2 and store the result in R1 again, but we could not add R1 and R2 and store the result in a different register, R3. So these codes actually fell into disuse. They were used because of memory constraints. Usually these became less important, so memory is cheap nowadays. And essentially two-address codes were replaced by three-address codes. So three-address codes actually give you more liberty because you are not constrained to actually reuse one register. So in three-address code you can use something like add the contents of register R1 and R2 together and store them in R3. And when you want to model the behavior of a two-address code, so a destructive change of one of the operands, then you can of course do it in three-address code by just using one of the operand registers as the target register explicitly in three-address code. And three-address code became very popular due to the rise of RISC architectures in the 1980s and 90s, because three-address code resembles a simple RISC machine relatively closely. So let's first take a quick look at stack machines. We've seen stack machine code offers a compact and storage efficient representation because we only need one address per instruction and the rest is implicitly operated upon on the stack. And this is one form of our one address code, and this requires some sort of mostly hardware support later on. And the compiler then assumes that we have a stack of operand which is present, and that arithmetic operands automatically operate on that stack. For example, they take, for an addition, the topmost two elements of our stack, remove them from the stack, add them together, and store the result on the stack again. So most operations in a stack machine take their operands from the stack and push the results back onto the stack, as I've just described. And of course you could do this for different arithmetic operations like subtract and multiplication. So sometimes you need to have additional operations then, because you need, for example, to change the order of operands in an expression. So if we need to keep to the stack discipline, we have a need for some new operations. So for example, a swap operation interchanges the top two elements of a stack, or we can have additional operations to just drop the top elements of a stack to throw it away, because we won't reuse its value, but we need the values further down in the stack. And there have been several stack machines that have been built. One machine that was relatively famous is the machine called Lilith. So this was a custom design by Niklaus Wirth, so of Pascal fame at the Zurich Institute of Technology, and this was especially built for running an intermediate representation, which was a stack machine representation of code written in his modular 2 language. And they not only built one, they built a large number of them, and actually had the students and researchers use them for many years at ETH Zurich for teaching and for research projects. Another machine came from the UK. This was called the Transputer. So the Transputer was thought as a node in a very large distributed network of these Transputer chips. They were very popular at the end of the 1980s, early 1990s to build. Back then were supercomputers. Nowadays, of course, your Raspberry Pi is faster. Those also had an internal stack machine architecture and a hardware stack. So what does stack machine code look like? We've already seen we have some sort of internal stack, so we know we have sort of stack operations. So we need to be able to put values on top of the stack, so a push operation for a stack, and we might need to remove values from a stack, a pop operation. And then we have general operations that only operate on the stack, and they implicitly then assume that the operands for this operation, like a multiplication or a subtract operation here, are already on the stack, and the result is then again pushed to the top of the stack. So here we have a stack that grows from the top towards the bottom, and let's take a look at stack machine code for this expression a minus 2 times b. So we know when we build a compiler for this, we first need to evaluate 2 times b to adhere to the standard operator precedence in arithmetic expressions, and afterwards we can subtract the result we obtained by our multiplication here from our variable a here. So for a stack machine, this means you would need to push the two parameters you need on your stack. So first you have a single address instruction here, so a single operand instruction, which pushes a immediate value 2 on top of the stack. And you have another one which pushes your operand b on top of the stack. Then you execute a multiply. Then you also need to push the operand a on the stack and execute a subtraction instruction. So let's take a closer look at what happens on the stack when we do this. So initially we just assume our stack is empty. So when we push value 2 here, we have value 2 on top of the stack, so we pushed it down here, and we have an unknown empty value here at the other element further down in the stack. So our top of the stack is always the topmost element here. That was all the push instruction did here. The next instruction is push b, so this might be a memory location or something. We won't go into detail of how to access these here. So this means when we push another element, the element that was at the top of the stack before is now pushed one position down, so our 2 moves from here to here, and we have a new element on top of the stack, which is b. So now we have our first arithmetic operation, our multiplication here, and multiplication implicitly removes both elements 2 and b from the stack, which leaves us with an unknown element here. It performs the multiplication and then pushes the result of 2 times b on top of the stack. So we have 2 fewer elements here, and then after the multiplication we only have one element, our result of our multiplication, on top of the stack. Okay, so then we push a. So 2 times b moves further down the stack again. We have a on top of the stack now. And finally we can execute subtract, which removes these 2 operands again and pushes our result here. Of course, this would be a number instead of our formula, on top of our stack again. And this means we would only need one operand for most instructions, and for arithmetic instructions that just consider the stack alone, we don't need an operand at all. So another example for a stack machine is one you might be already familiar with, or at least you have used it so far, and this is Java bytecode. So Java bytecode is also sort of an intermediate representation because it's generated by the Java compiler, but it usually cannot be directly executed by the CPU, so it needs to be either interpreted, which is slow, or compiled, for example using a just-in-time compiler in the JDK, or even an ahead-of-time compiler, which is what happens with the alternative implementation of Java bytecodes on Android nowadays. So usually this is represented in binary form, but this is a bit hard to read, so we give you an example that's actually the disassembled instructions for this bytecode. And it's called bytecode because most instructions are actually 1 byte in size. So let's take a look at this Java method here, so public static void main, and well, we ignore the arguments here, and this just declares 2 variables a and b, initializes them, and then assigns the sum of these to a third variable int c. So if you compile this using a Java compiler, you get your bytecode file out, so your class file, and you can, for example, if you call this test.class, you can actually disassemble your Java bytecode using the tool java p-v, and then you get information about your Java bytecode. Now Java bytecode contains some additional information in addition to the instructions themselves, so some structural information, like for example the name and the signature of functions, and a number of flags and descriptors here. So for example we give the information that we have a public and static method here. So our code now, well, says, okay, we have some stack use, we have some locals, we have argument size, and what we do now here is we use these machine instructions. So our first machine instruction here, you see we don't have any variables anymore. This just says iconst1. So iconst1 means we actually generate this and store this constant here. The same for our constant 2 here, which we store then. Then what we do is we load our operand 1 onto the stack, which we just stored here. Then we load our operand 2 on the stack, which we just stored below here, which are the constants 1 and 2 by coincidence. Then we execute iadd, which removes these 2 top elements on the stack and pushes the result on the stack, and this is then stored here into the location of our third variable here. So that's very similar to what we've seen before. And if you're interested, there are actually a number of books also describing what's happening internally with Java bytecode, and there are also books describing what's happening on Android with their different virtual machine implementation. So when we don't want a stack machine, the most common alternative, as we've seen, is a 3 address code, so we won't discuss 2 address code in detail here. So 3 address code, or simply TAC. So most operations in 3 address code have the form that we have 2 operands here, j and k, and they're combined using some sort of operator, which might be an arithmetic instruction, for example, and we assign the result of this operation to another variable or to another identifier I here. So we have 1 operator, 2 operands, and 1 result here. Some operators will need fewer arguments, so if we have an immediate load or a jump operation, we only need 1 operand, for example. Sometimes, on the other hand, we need an operand with more than 3 addresses, but this is a detail we don't need to consider here. 3 address code is less compact than the stack machine code, but it's still reasonably compact because most operations are just a 4 tuple, so they consist of 4 items, which means we have to describe an operation and we have to provide 3 names here to describe the complete operation, including the operators and the result. Both operations and names are drawn from limited sets, so the set of identifiers or the set of symbols in your symbol table. So an operation, there are not that many operations, typically require 1 or 2 bytes, and the names are typically represented by, as we said, integers, like we've seen also in Java, that Java just enumerates the integers, or we can use table indices, for example, to a symbol table. In most cases, 4 bytes are usually enough to store a single 3-address code instruction. So if we look at an example for 3-address code, we see that 3-address code resembles a RISC-like register machine. So operands have to be loaded into registers. Operations other than load or store operate on register values, and the result of an operation is again delivered in a register. So we cannot store, for example, the result of an operation directly into memory location. We have to store it in a register first and then store this register contents into memory if we want to have this value stored into memory at all. We have limited constraints for naming and allocating registers compared to real machines, so we might have a machine that just has the real variable names here, for example A and B as variables here, and then has some intermediate temporary names here in between, and we don't have constraints, for example, for many intermediate 3-address code representations that constrain the number of registers. So this makes it a bit simpler, because we only need to consider real-world constraints later on when we generate real machine code. So 3-address code for our arithmetic expression a minus 2 times b might look like this. So we first load our constant 2 into temporary 1, then we load our constant b into temporary 2, then we execute our multiplication operation, now using the 2 intermediate results, because we know these operations can only operate on our internal registers here. So 2 is just a constant, b is a variable that might be somewhere in memory. We've loaded them into these 2 temporary registers, we multiply the result, and we know we need to store the result of our multiplication in yet another register, which is T3 here, so we can just increment the index of our temporary register variable here every time we need a new one. And finally we need to consider a here for our subtraction, so we copy a into T4, and then we subtract our value of a, which is in T4, from our intermediate result 2 times b, which we stored in T3, and finally assign this to T5. So what we don't have here is storage here, so if we want to store T5, we would need a store instruction again. Now if you look at the right hand side example here, this is ARM assembler code, so for a real ARM processor for the same expression, and if you look closely, well, it looks rather similar. So for example, we could implement our first instruction here by moving our constant 2, so this is indicated by the hash mark in ARM assembler, to a register R1, and moving, as you know already, it doesn't move a value, it copies a value over into that register. Then we need some access to a variable here, so this is a bit more complex in ARM, because we first need to get the address of b, which is the equals operator here. So we load the address of b into register 2, and then we dereference this pointer, so the address in R2, which is indicated by these square brackets here, and copy the result into R2 again, because we don't need that address again, so we can reuse that register. We did this here just to keep the indexes of our registers consistent with the indexes of our virtual temporary registers on the left hand side. Now we can do a multiplication here, so we know we have one result here, and that should be R1, sorry, typo, and the other in R2, so we can multiply R1 and R2 together to get R3. Then finally we need to load variable a from memory, so we do the same for a as we did for b here, using R4 now, and finally we can do the subtraction, so we can subtract R3 from R4 and store the result in register R5. So you see the syntax is different here, but essentially the operations performed and the parameters of the operations are identical. So one real-world example for a 3-address code that's used in common compilers is the intermediate representation that's used by the LLVM toolchain. So LLVM IR is also called bitcode, and that's a bit of an exceptional intermediate representation. So LLVM retains type information in the 3-address code, so it's a type 3-address code. So for example, on the right hand side we have the LLVM IR code for this C function here. So this is a function foo that takes two parameters a and b, both integers, returns an integer, and the return value is again our expression a minus 2 times b. And you can compile this down to IR code, and if you have Clang installed on your machine, so you can install it on Linux, or you have it installed already on your Mac when you install the developer tools, you can generate this intermediate representation code with Clang-S. -S usually is a compiler option to emit assembler source code, but if you tell it to emit LLVM, which is the intermediate representation for your foo file, it gets you this information here, so you have the intermediate representation. So what are we doing here? First we have some information about the function we compiled, so we say we define something which returns a 32-bit integer here, so we see we have a typed 3-address code which already gives you the width of your instruction. Then we call this one foo, so that's a symbol here, and this takes two integers here, and what we do in here is first we need to allocate memory for parameters here. So we allocate memory for what we call %3 and %4 here. So this is an allocation of a 32-bit integer with an alignment of 4 bytes. So we have two variables here aligned. And first we store these parameters that were passed, these are called 0 and 1, into our local storage cells, our local memory cells for our local variables a and b. This is what these stores here do. And you see also our pointers are typed here, so it's a pointer to an int32, for example. So a store takes a register here, so the first parameter that was passed to foo in 0, and stores it in the address, so that's why we need a pointer here. That is the address of our allocation of memory here. And again, we specify an alignment. We do the same for our b here. And now we need to load our values. You see this is very unoptimized, so it just assumes always that we need to fetch and store values explicitly, and we can optimize this later. So we see we need an additional intermediate register %5 here. So now we load the value that was just stored into a memory location that was pointed to by %3. We load this here from our pointer as an integer 32-bit into %5, so this would be our value a here, and then we load b again from the memory location %4 into register 6. And finally we can do a multiplication here, so we do a 32-bit multiplication, and we multiply %6 by a constant 2 here and store it in register 7. And finally then we can do the subtraction here, so we subtract our intermediate result of our multiplication here, which was stored in our virtual register 7, from our value a here in register 5, so a minus 2 times b, and we store this in register 8. And finally we want to return this value here, so we have a return instruction and return a 32-bit integer, which is the value we just got into our virtual register 8. So that's exactly what happens here, and we've also described this on the left hand side here, so to see where our copy and memory dereferencing operations take place. So this is very unoptimized. So for example, you wouldn't need to store these intermediate values, but you could maybe reuse %0 and 1 directly. But later stages in our IR, and we'll take a close look at all the optimizations that can take place, can of course figure out that some of these values can actually be directly used because we have a data flow analysis here. And so when we really generate machine code from this, we can remove a lot of these instructions because they're not actually needed for the semantics of our program. So that was a quick introduction to different kinds of intermediate representation and giving you some examples for this. And in the following lecture we'll talk more about intermediate representations, so how to efficiently implement them, especially in a form that's very common, which is called the Static Single Assignment or SSA form. And here are finally some references on intermediate representations. So there's a nice survey paper from 2013. Here's a paper about the Lilith stack machine hardware workstation that was built at ETH, so that was a PhD thesis at ETH. There's an interesting book that's already 30 years ago old again, which is called Stack Computers, The New Wave. Well, this new wave was a very flat wave, obviously, so it didn't really manage to gain much attraction, but still it's an interesting book to read, and it's freely available at that address here. And there's also the Java VM specification, which might be interesting, and there's a language reference manual for LLVM if you're interested in the details of the intermediate representation. So that's all for today. So in upcoming lectures we'll talk more about intermediate representation and then how we can use these intermediate representation to actually optimize our code. Thanks for listening, and until next time, bye.